of loading. Okay. When there are a number of stages from sensor directly to the display or rather monitor or a microprocessor, etc., intermediate stages are there, and the signal is passed from one stage to other. Okay, so each component has its own impedance. Okay, so the output impedance of the one stage acts as input impedance to the next stage. Okay, so this is the concept for various stages then. Okay, and if the input impedance to any stage is higher, okay, ideally input impedance of any device should be as large as possible, whereas the output impedance should be as low as possible. Okay, so if it is reversed, then that is called a loading effect. Okay, so input impedance if it is low, then that will be a difficulty passing the signals. The earlier stage will load the next stage. Okay, here for example we have a sensor and an amplifier. Okay, so input of the sensor, or rather output of the sensor is given to the as an input to the amplifier. So let us discuss the loading effect. Before going to loading effect, we must know we will be using Thevenin's theorem thereafter in some applications here. Okay, so let's discuss Thevenin's theorem before going to loading effect. What the Thevenin's theorem states? Thevenin's theorem states that any linear bilateral network containing any number of sources between two terminals can be replaced by a single voltage source and a single resistance or single impedance. Okay, in case of DC it is resistance, in case of AC it is impedance. Okay. So the voltage source value is given by the open circuit voltage between given terminals, and the resistance or impedance value is given by the equivalent impedance between given terminals. So this is the given circuit, okay, given network, and points A and B are there, and load resistance, and that can be converted to its Thevenin's equivalent consisting of VOC and RI, or VOC and ZI if it is AC circuit. Okay, and this is RL or ZL. In that case, output voltage is given by, generally in BWE or in network theory, what we did, we found the load current. Here we want to find out the voltage, right? So load voltage will be RL upon RI plus RL into VOC, because it's a simple series circuit, voltage divider circuit, and voltage across internal resistance is given by RI upon RI plus RL into VOC, right? So VL is RL upon RI plus RL into VOC, and RI is RI upon VOC, RI plus RL into VOC. Okay. So substituting this, VL can be calculated at no load voltage VOC. Suppose RL is absent, the terminals are open, so whatever the VOC will appear between A and B, so that VOC. Okay, and when it is loaded, some drop will be across this. Okay, so that drop is VRI, and VRI is substituted here. Okay, this value substituted here will give VL is equal to VOC into 1 minus RI upon RI plus RL. So this should be understood then. Thevenin's theorem. We are finding the output voltage. Okay. In case of no load, output voltage will be equal to the source voltage VOC. In case of load connected to the circuit, the output voltage will be less than VOC, or less than source voltage. And it will be by the factor RI upon RI plus RL into VOC. This much should be subtracted from VOC, and then we will get VL. And of course, VL will be less than VOC always. And this drop, will depend upon the relative values of RI and RL. Okay, understand that if RL is far greater than RI, okay, RI is negligible, RL is far greater than RI, then this will be very less because RL has a higher value. RI upon RI plus RL will be negligible, and the drop will be there, so that VL will be approximately equal to VC. But if RL and RI are comparable, say RI is equal to RL, for example, RI and RL are equal. So if this is 10 volt, there will be 5 volt drop in this, and remaining 5 volt will appear across this one. So out of the 10 volt uh, source voltage, what we are getting as VL is 5 volt only. So that is the importance of RI and RL, right? So to avoid this, RL should be made far greater than RI. Okay, that's the method then. Okay. Let's go to the loading effect. Loading, it is an important effect in which one circuit loads another circuit in the system. What is the effect of loading? It introduces uncertainty in the amplitude of voltage as it passes through the process. What does it mean? Can we predict the voltage VL if RI is present? Okay. No, because the drop across RI will depend upon current through this, and current depends upon RL, right? So as the current changes, the drop changes and output voltage also changes, so it becomes unpredictable. VL becomes unpredictable. Okay, so that is what it means. It introduces uncertainty in amplitude of voltage as it passes through the process. Okay, so here again the same is explained. Okay, so this is sensor. Okay, X is the sensor. Vx is the, this is Thevenin's equivalent of the sensor. Vx and Rx is the open circuit voltage, or VOC for sensor, and internal resistance of the sensor. So here the output voltage Vy is there across load resistance. So Vx will be, as in this case, VL is VOC minus this. So this will be Vy is equal to Vx into 1 minus Rx upon Ri plus Rl. Same formula, only notations are changed, right? It's the same circuit. So uh, what actually, how does it affect next stage? See in this one. Okay, this is an example. Through this example, we will experience the effect of loading. Okay, just a minute. Direct examples are taken. Okay, we have an amplifier. See the problem. What is written here? An amplifier output voltage, that is, amplifier outputs the voltage, that is 10 times the voltage at its input terminal. Okay, what does it mean? If 1 or rather 2 volt is the input to the amplifier, it increases it 10 times. So output will be 20. If it is 3, input is 3 volt, output will be 30. What is 10 then? 10 is the gain of the amplifier. Okay, so amplifier gain is given as 10. Okay, so it has an input resistance of 10 kilo ohm. Okay, so these are the properties given of amplifier. Where is the amplifier? See, this one is the amplifier. Its gain is 10, and its internal resistance, right, is 10k, right? It has an input resistance of 10k. So 10 gain is 10, and input resistance is, internal resistance is 10k. A sensor outputs a voltage proportional to the temperature with a transfer function of 20 millivolt. Sorry, this one is misprint, double. 20 millivolt. Is the screen visible?
Yes, sir.
Yes or no?
Yes, it is visible.
Okay. See, so sensor outputs a voltage proportional to temperature with a transfer function of 20 millivolt per degree Celsius. Okay, sensitivity of the sensor is given. Okay, the temperature sensor like RTD or thermistor or thermocouple is given, and its sensitivity is given as 20 millivolt per degree Celsius. So 1 degree change temperature creates a change of 20 millivolts in output voltage of the sensor. So that is the sensitivity of the temperature sensor. Okay, the sensor has an output resistance of 5K, right? So this is the output resistance of the sensor, right? If the temperature is 50 degrees Celsius, find the amplifier output. So T here given is 50, and we want to find out the output voltage here. Okay. Meanwhile, the sensor parameters are given as 20 millivolt per degree Celsius is the sensitivity, and 5K is the output resistance at output terminals of the sensor. Whereas the internal resistance or input resistance of amplifier is 10K and gain of amplifier is 10. Okay. So with this given data, we have to find out output voltage for an input temperature of 50 degrees Celsius. Let us consider now only sensor. Okay, only sensor. So under no load condition, meaning there is no amplifier connected to the output of the sensor, the output of the sensor Vt will be the sensitivity into temperature. What is the sensitivity? 20 millivolt per degree Celsius, and the temperature is 50 degrees Celsius. So output voltage of the uh, sensor will be 20 into 10 raised to minus 3 millivolt per degree Celsius into 50 degrees Celsius, that is 1 volt, right? So if 50 degrees is given here, output voltage Vt at the output of sensor will be 1 volt, right? But under loaded condition, this will not be equal to 1 volt. It will be less than 1 volt due to loading effect. Let us see how it is less than 1 volt. This is under no load condition where amplifier was not connected at all across this sensor. Now what happens? Okay. Now the amplifier is connected and amplifier has in the input resistance of 10K. So in addition to output resistance of the sensor as 5K and input resistance of the amplifier 10K, it becomes a series circuit like this with Vt, right? So Vt on no load was 1, right? On no load it was 1. That is the Thevenin's voltage VOC. VOC is 1. This is Ri of this sensor, and this is Ri of amplifier. Okay. So using the formula stated here, Vy is equal to Vx into 1 minus Rx upon RL plus Rx. What we get here is that, okay, V in, right, here, the input voltage here is Vt, output voltage here, output voltage at this point into 1 minus 5K is this resistance of sensor divided by 5K plus 10K, this plus this resistance. And open circuit voltage Vt we have already found out in last step as 1 volt open circuit voltage. So keeping Vt is equal to 1 volt, what we get input voltage to the amplifier to be 0.67. Are you getting me? So this is the input voltage. Okay. Actually, here it was 50 degrees Celsius and at no load it was 1 volt. But with 50 degrees Celsius and amplifier connected, there is a loading effect which will reduce the input to the amplifier from 1 volt to 0.67 volt. So if the input to the amplifier itself is 0.67, then with a gain of 10, it will output of the amplifier will be 10 into 0.67, that is 6.7 volts. In ideal condition, without any loading effect, if this is 50 degrees Celsius, here it should be 1, and here it should be 1 into 10, that is 10 volt we should get in ideal condition without any loading effect. But since this has an output resistance of sensor has an output resistance of 5K and amplifier has an input resistance of 10K. These combinedly form a circuit and drop the voltage from 10 volt ideally to 6.7 volts practically. So this is the loading effect. Are you getting me? Okay. If suppose this resistance of uh, sensor sensor resistance is made negligible to 10K, okay, negligible to this second stage resistance. Negligible meaning say it is 50 volt. Will it affect 50 divided by 15K? Okay, this term will be negligible and V in will be approximately equal to VT. Are you getting me? So we should uh, reduce this resistance in comparison with this. That is the method adopted. What we can say, rather this can reduce our loading effect. So output resistance of earlier stage should be far less than input resistance of the next stage. Okay, rather we will say input impedance of the next stage should be far greater than the output resistance of earlier stage. So this 10K should not be comparable with 5K. These are the comparable values. If this is made very less or this is made very high, suppose this is 1000K, right? This resistance is how input impedance or input resistance of the amplifier is 1000K or 1 mega ohm. So 5K can be neglected. So 5K divided by 1 mega ohm, this term will be negligible and V in will be equal to VT and V out will be approximately equal to 10 volt in that case. Okay. So this is what is the loading effect. Output resistance of earlier state should be far less than input resistance of the next stage. So this will reduce the loading effect. May I know, is the loading concept clear? Can I have some answers? Loading effect. Is the concept clear about loading effect? Please unmute and answer. No, I didn't get any answer. Am I audible? Am I audible?
Yes, sir.
So what I was asking was, is the concept of loading, you understood it?
Yes, sir.
Sure now. Any
Yes,
other
sir.
answer? Please unmute and answer, please. Loading. The next stage, earlier stage is loading the next stage. Okay. So what should I assume then? Okay, let's continue. Okay, this is an important as signal amplitudes are where the signal amplitudes are important. Okay. Where the loading effect can be neglected if enough signal is left after loading, like in case of frequency measurement or digital signal. Okay, 0 and 1. In case of digital TTL circuits, you might be knowing that there is a range for 0. What is that range? From 0 to some value, 0 volt to some value. I think it is 1.8 volts, something like that. If I'm correct, 0 to 1.8 volt, the level is considered at 0, and 2.7 to 5 volt level is considered as 1. Okay, so if the drops in voltage are within this range, that won't affect. So loading won't affect digital circuits 0 and 1. Similarly, for frequencies also, if there is no distortion as such in an amplitude, rather frequency, then loading effect can be neglected from one stage to other. But where the amplitudes are in analog circuits, amplitudes are important. Signal amplitudes are important, like in sensors and then amplifiers and then microprocessors and etc. Where the amplitudes are important, in that case, loading effect should be and we should try to minimize this loading effect. Okay, let's have one other example. Okay, uh, what the example says, an unloaded output of sensor is a sinusoid. Okay, input is given to the sensor, some type of sensor, and output is a sine wave. Okay, the frequency of sine wave is 200 hertz, and the amplitude of the sine wave RMS value is given. Okay, 5 volt, right? Uh, its output impedance is 2000 plus J600 ohm, right? Now this is the output impedance of given sensor. Okay, output voltage amplitude is 5 volts and frequency is 200 hertz, right? And output impedance of the sensor is 2000 plus 600 J600. Okay, but it's an AC circuit then, right? Output is AC. Of 0.22 microfarad is placed across the output. So this capacitor is acting as a load then for the sensor, right? So this capacitor of 0.22 microfarad is acting as a load for this sensor. Okay? What is the sensor output voltage? Amplitude. Okay, so it means that what is the voltage across capacitor? Load voltage. Sensor output voltage is the load voltage because capacitor is connected across the sensor, right? So how to solve this then? Okay, uh, let's have this image then. Okay, is it visible?
Yes.
Is this
Yes,
visible?
sir. Yes, sir.
Yes. So what is given? Frequency of output signal, it's AC and frequency is 200 hertz. RMS value of AC sine wave is given as 5 volt. So this is the sensor output. Output impedance of the sensor is given as 2000 plus 600 J600 volt. So in polar form it will be 208 angle 16.69 ohms. Whereas the output ZL is equal to uh, capacitor, okay, capacitive reactance rather. C is given as 0.22 microfarad, and therefore ZL will be XC, which is given by 1 upon 2 pi FC. F being 2000 or 200 hertz, the ZL becomes output impedance. ZL becomes this ZO is of the sensor, ZL is of capacitor, right? So ZL becomes 1 upon 2 pi FC, 3617 ohms. ZL is 3617 ohms. So output, so this then is a Thevenin circuit now and a series circuit. So VO across ZO, that is to be found out. What is the sensor output, that is to be found out, right? What is asked? Let me. What is asked? Sensor output voltage amplitude. Sensor output voltage amplitude. No. What is to be found out? This is the drop in voltage rather. Okay. This is not the load voltage. Load voltage will be 5 minus this value will be the voltage across the load. Okay. Let's find the drop across the sensor. Drop across the sensor, that is output impedance across the sensor. So drop across the sensor is ZO upon ZO plus ZL, right? ZO we have calculated to be 2088 and ZL we have calculated 3617. So VO, that is drop across the sensor is 2088 divided by 2088 plus 3617 into V, which is 5 volt, and this drop comes out to be 1.83 volts. Okay, and of course the remaining voltage, this much voltage, 1.83 volt is dropped across this, and remaining, okay, 3.17 volt will be available across the load resistance. Ideally, if this were not there, ZO were not there, then all 5 volts would have been across the load resistance, and then there would be no loading effect as such. But output impedance of the sensor being there, and which is bound to be there, we can't avoid it. Sensor is a physical device, and each physical device will come with its properties, right? We can't control these properties because these are the natural devices, right? So output impedance, some of the output impedance is bound to be there. So ZO is 2088, and voltage drop in this 2088 is 1.83, while remaining voltage 3.17 will be available across load, which should ideally be 5 volt. Instead, we are getting 3.17. Is the concept understood then? Let me have some answer.
Yes, sir.
Loading effect is understood then. Okay?
Sir, how can we minimize this loading effect?
Pardon?
How can we minimize this loading effect?
That's what I said, no? Either ZL should be increased far greater than ZI. This is
Okay.
output impedance. Okay? Or this should be reduced in comparison with this. Anyway, the input impedance of next stage should be so high that output impedance of earlier stage should be negligible in comparison with that. Okay, that's why we use, you must have studied in DLIC, op-amp. Okay, why op-amp is so popular? Because its input impedance is very high. Ideally, it is infinity, but in practice also it's order of the mega ohms, right? So that's why it is popular, because whatever is the input impedance of the device connected to its input terminals, the input impedance of op-amp being very high, the earlier stage output impedance becomes negligible in that case, and loading will not occur. Is it clear?
Yes, sir.
Okay. Okay. So input impedance of the next stage, which is ZL here in this case, if we connect the amplifier or something like that, here we have connected capacitor, but next stage can be amplifier, okay, as in previous case. So amplifier input resistance should be so high that this should be negligible to that. In earlier example we have seen, that, okay, this is 10K and this is 5K. They are comparable. This is 10K and this is 5K. If this is 1 mega ohm or 10 mega ohm, this would be negligible. And in that case, loading effect can be reduced. Is it clear?
Yes, sir.
Okay. Okay. So this was the next example then, right? Now some signal conditioning circuits we will discuss. Okay. Mainly three types of passive circuits. The signal conditioning circuit, as we said, as we already said, that it can be passive circuit like resistor, inductor, capacitor circuits containing networks containing resistor, inductor, capacitor. These are called as passive components, right? Whereas the transistors and amplifiers and op-amps and all these semiconductor devices are active circuits. They are called as active circuits, active components. Okay, so signal conditioning circuits can be either passive circuits or active circuits. Okay, let's consider first passive, and then we will discuss signal conditioning using most widely or popular component op amp. Okay, that will be later. Now it's signal conditioning using passive circuits. And the main three types of passive circuits used in analog signal conditioning are voltage divider circuit, a bridge circuit, and various types of filter circuits. Okay, so what is voltage divider circuit? Okay. Let us consider one by one. Voltage divider circuit. It's very simple. Okay, the two resistances, or in AC circuits, it will be impedances then. R1 and R2 are the two impedances, rather resistances, connected in series across some voltage Vs, right? This is voltage Vs and this is ground. So applied voltage is Vs, this is 0 and this is Vs. Whereas R1 and R2 are the two resistances connected like this. This forms a voltage divider circuit. Okay, and uh, what we want is output is taken at the midpoint between this R1 or R2, the connection between R1 and R2. This is VD. Okay, so this voltage between this connection, output voltage between the ground and this point is VD. That is the output voltage we are taking. Okay, and this will be, as we know, in voltage division in series circuit, larger the resistance, larger is the voltage across it. Smaller the resistance, smaller is the voltage across it. Right? So, in a series circuit, voltage is directly proportional to the value of resistance. Larger the resistance, larger voltage across it. Smaller the resistance, smaller voltage across it. Okay? How is our VD given by? VD is across R2. VD is across R2. So it is R2 upon R1 plus R2 into Vs, applied voltage, right? And so this is the output voltage between the ground and this point. Okay. Now, what we are interested in is we are considering sensor as one resistance. Okay. Why we are discussing this is that one of these two registers is the resistance of sensor that we are using in instrumentation system, right? So what can be the sensor? Sensor can, as we say, temperature sensor like RTD, it can be thermistor, it can be thermocouple, or it can be a strain gauge, it can be a load cell, right? Any sensor can be there, right? So one of these two, R1 and R2, is the sensor resistance. Okay? Either R1 or R2 can be a sensor whose resistance varies with some measured variable. Okay? Like in RTD thermistor or thermocouple thermistor, the resistance varies with temperature. So as the temperature varies, resistance varies. In case of strain gauge, uh, as the stress deformation of that strain gauge occurs, dimensions, length and breadth of that strain gauge changes, its resistance changes. With applied force, the dimensions of the strain gauge element change and the resistance changes. Okay. Similarly, for load cell, applied force is varied, then its resistance of the strain gauge is changed, and then that is what is our sensor. Okay. So R1 or R2, anyone can be sensor with which can change with measured variable as temperature, force, pressure, or some other variable. Okay. So this is what is the voltage divider circuit. Why we are why this is important? Because one of the arm of this voltage divider is the sensor circuit, sensor element rather. Okay. When using voltage divider, these points must be kept in mind. Which are those? Variation of VD, the output voltage, with either R1 or R2 is non-linear. Okay. The first thing is that R1 itself can be linear or non-linear. Like in thermistors, we have to linearize it. In case of RTD, rather it's almost linear within the range. But in case of thermistors or strain gauges or other values, the output is non-linear. Change in resistance is resistance itself is non-linear. But even though resistance varies with the parameter linearly, VD will not vary linearly. It's because of the formula. R2 divided by R1 plus R2 into Vs. It's not a linear formula, right? R2 changes, this value also changes, and the relation between VD and R2 then will not be linear. Okay, so even though R1 and R2 varies linearly with temperature, VD will not vary linearly with resistance. Okay, so there will be certain non-linearity present there. Effective output impedance of the voltage divider circuit is the parallel combination of R1 and R2. This may not be necessarily so high, so that loading effect must be considered. What does it mean? Okay, consider this circuit. What is the output resistance or output impedance between VD and ground? This point is say X and ground. Okay, we have to calculate RTH then. How to calculate RTH? We have to short these two, remove this Vs and short these two terminals, right? While calculating RTH in Thevenin's theorem, what we do, we remove all the voltage sources, replace them by short circuit. If there is a current source, we replace it by open circuit, right? So here, Vs is the source that we are removing and shorting it here. So when we short these two terminals, R1 and R2 come in parallel, and then the resistance at the output terminals VD, between VD and ground will be parallel combination of R1 and R2. That's what it means. Effective output impedance of the voltage divider circuit is the parallel combination of R1 and R2. This may not necessarily so high, so the loading effect must be considered. Okay. Of course, the output impedance depends on the relative values of R2 and R1. Okay. So if they are comparable, then output impedance can be low. If they are output impedance should be actually here it should be low then. Okay, so loading effect will be there. Current flows through both the resistors and therefore power will be dissipated by both, including sensor, and therefore power rating of both sensor and resistor must be considered. While selecting, okay, while selecting a sensor, power dissipation is an important criteria. Okay, power dissipation depends upon the current drawn by the circuit. Okay, suppose load is some load is connected to amplifier, and amplifier input is given from the sensor. Okay, we want to select the sensor. The load is such that it requires 10 milliamperes, rather 50 milliamperes suppose. So, and amplifier gain, current gain is say 5. So input current to the amplifier is 2 milliamperes, 50 by 2, that is 50 by 5, that is 10 milliamperes. Okay, so the sensor should have a capability to withstand a current of 10 milliamperes, and whatever the power dissipation due to this 10 ampere, okay, the sensor should withstand that much power dissipation. So when there is a series circuit of sensor resistance and input resistance of amplifier, both will be dissipating the power, and the power dissipation capacities of both should be considered while selecting the sensor and even the amplifier also. That's what it means. Okay, what is the meaning? Current flows through both the resistors, and therefore power will be dissipated by both, including the sensor. Therefore, power rating of both resistor and sensor must be considered while selecting the sensor. Okay. Otherwise, if the more current is drawn from the sensor, it may burn out, it may be damaged. Okay. Let's consider this example then. Okay. What does it say? A voltage divider circuit is there. It has R1. Very simple, all values are given, right? R1 is 10K. Source voltage is given as 5. So R1 is 10K. Vs is 5. Suppose R2 is the sensor whose resistance varies from 4K to 12K. So this is the sensor, okay? The thermistor or RTD or strain gauge or something like that, okay? So the resistance R2 of the sensor varies with the parameter like temperature. So with minimum value of temperature, resistance is 4K, and with maximum value of temperature, the resistance R2 of the sensor is 12K. Okay? Then find the minimum and maximum value of VD, range of output impedance, and the range of power dissipated by R2. Okay. So with respect to this sensor, we want to find out VD minimum and maximum for the range of 4K to 12K, range of output impedance. Output impedance is the parallel combination because Vs removed, this shorted, then R1 parallel with R2 gives the output impedance, right? So range of output impedance meaning minimum value of R2 and maximum value of R2 in parallel with R1. That will give the minimum and maximum output impedance, right? And the range of power dissipation by R2. Okay. So power dissipation can be given by I square R or V square by R. Okay. So V square by R2 will be the power dissipation. V is VD. So VD square by R2 is the power dissipation. Rather, Vs square by R2 is the power dissipation. Right? So let's see how it is solved. Okay. Let's go to the solution then. Just a minute. Okay. This is the circuit R1, R2, and VD. R1 is given as 10K, Vs is 5 volt, source voltage, R2, range of R2 is 4 to 12K, right? So what we want to find out, VD minimum and VD maximum, output voltage. Second, range of output impedance, that is resistance between this point and ground, okay, minimum and maximum. Okay, and range of power dissipation, minimum power dissipation and maximum power dissipation by the sensor resistance R2. Okay. Number one, what is number one? VD min and VD max. R2 minimum is 4K, that is 4 into 10 raised to 3. Okay, so VD minimum will be R2 min divided by R2 min plus R1 into Vs. So it's a voltage divider circuit. R2 divided by R2 plus R1 into Vs. So 4 divided by 4 plus 10 into 5 comes out to be 1.43. So minimum output of the sensor, output of the sensor comes out to be 1.43. This is actually very important from practical point of view because many of you might be doing the projects, sensor based projects, temperature sensors or pressure sensors or force sensors, etc. Okay. So when you are using sensors or designing the circuit, okay, so you must know minimum when you directly buy the sensor from the market, okay, you must see its minimum output voltage and maximum output voltage, the range, right? So that is specified there, and according to your requirement, you should purchase that sensor. Otherwise, if the range of the output minimum and maximum output voltage of the sensor doesn't match your circuit, that sensor will not be useful in your project. Okay, so how to calculate it? Okay, minimum and maximum resistances are given. So VD min comes out to be 1.43. Similarly, VD max will be R2 max divided by R2 max plus R1 into Vs, and it comes out to be 2.72 volts. So with some parameter, temperature, pressure, or force, or something like that, or stress, varies from minimum to maximum, the sensor output voltage changes from 1.43 volt to 2.72 volt. Okay, this you have to give it to microcontrollers or ADC, something like that. Then you have to again use amplifiers or attenuators and some other circuits. So range of output voltage of the sensors for given variation from 4K to 12K of R2 sensor resistance is 1.43 to 2.72 if voltage divider circuit is used. So what next then? What is next is found out? Minimum and maximum value of VD is found out, 1.43 and 2.347, something like that. Okay, 2.7. Range of output impedance, minimum output impedance and maximum output impedance, right? Okay. Next part is this. Okay. Output impedance is the parallel combination of R1 and R2, as we say. We remove ES and we short these two terminals and find the equivalent impedance between these 2 points A and B where output is taken. So this is R1 comes in parallel with R2. So with R2 minimum as 4K, it will be 4 divided by 4 plus 4 into 10 divided by 4 plus 10. Are you getting me? It's just parallel combination. R1 R2 divided by R1 plus R2. So 4 into 10 divided by 4 plus 10 is equal to 2.86 kilo ohms is the minimum output impedance. Whereas R max, that is maximum output impedance, will be maximum resistance is 12K and 12 into 10 divided by 12 plus 10. So it gives 5.4 kilo ohms. So minimum output impedance is 2.86, maximum output impedance is 5.45K. Whereas we want the power dissipation, minimum and maximum range of power dissipation. So P min will be V square by R. So VD min squared by R min. VD min, what is VD min? VD min is 1.43. So 1.43 square divided by 2.86 into 10 raised to 3 comes out to be 0.51 milliwatt, right? Whereas 2.7 VD max divided by R2 max is 12K. So VD max square, sorry, this has to be squared, VD max square, V square by R. So VD max square divided by R2 max. VD max square is 2.7, whereas R2 max is 12K. So VD max square divided by 12 into 10 raised to 3 comes out to be 0.62 milliwatt. So the range of power dissipation of our sensor will be 0.51 milliwatt to 0.62 milliwatt. Okay, so this is how a sensor should be selected while using the voltage divider circuit. Okay, let's go to the presentation again. So this is what is about the voltage divider circuit. What next? Next circuits are the bridge circuits. Okay, okay. This is also very important. Bridge circuits are very important and very practical one. Okay, bridge circuits are very practical because in instrumentation, bridges are always used at the sensor level. Okay, in fact, one or more arms of the bridge are the sensors. Okay, RTDs and thermistors and strain gauges and load cells and all whatever the sensors, thermocouples, etc. They are the arms of the bridges. Okay, okay. The bridge circuits are used to convert impedance variations into voltage variations. Okay. Suppose the application is such that we have a cantilever beam. Okay, and if a force is applied, load is applied to the beam, okay, and we want to know how much is the bending. Okay, So what we do in that case, we fix the strain gauge. It's a flat film type device. So that film type device is applied to, it is fixed to the beam. And when the force is applied, the dimensions of that strain gauge changes. It changes its resistance. And this resistance, the strain gauge is a part or arm of the bridge. So bridge becomes unbalanced and it gives some output voltage. This output voltage is then amplified or attenuated and all conditioning is done. And the stress and strain in the beam can be calculated. Okay. You must have seen the weighing machines. Okay. Load cells are used there. When we stand on the weighing machine, okay, it puts pressure or force that changes the resistance of load cells, right? And it gives the output in terms of voltage, and rather it moves the dial on the pointer and shows the weight, or it can display digitally the weight. Okay, so these are the some types of sensors, and these sensors are used in arms of the bridges. What they do, they convert the impedance variations, change in impedances like resistance, just we have seen, into voltage variations. Resistance changes, bridge becomes unbalanced, and output voltage changes. Okay? Bridges are also used in precise static measurement of impedances. Okay? Another application we'll be using for uh, sensor measurements. Okay, sensor measurements. There are two types of bridges depending upon the supply. Okay, and the values of parameters used. If it is only resistive bridge, then and the supply is DC, then it will be a DC bridge. In case of AC bridges, supply is AC, and the components will be impedances rather than resistances. So DC bridges are with resistive bridges with DC supplies. AC bridges are impedances, impedance circuits with AC supply. Okay, so bridge circuits in details that we will discuss in next lecture, right? Bridge circuits and various other circuits, filters, etc. in coming lectures. Let me mark the attendance. I think everyone is understanding the basic concepts. I assume that. Let me mark the attendance. Okay, I marked the attendance. Thank you very much for patiently listening. I hope you are understanding this.